lines of best fit. So I'm once again going back to the college classes to get these done. So again, scatterplots and lines of best fit. So there's a lot of stuff in this one, so this one's probably going to be a pretty long one to watch. But we're going to look at what is a scatterplot, what is the different aspects of a scatterplot, what is a correlation variable, what does a correlation variable mean, what is the difference between correlation and causation, how does it fit, how do we find a line of best fit, and what are things like the residuals and the coefficient of determination. So the very first thing that I want to look at is what is a scatterplot. And a scatterplot is a graph that relates two variables to each other. So essentially we have, if you look over here, you have days related to weight. Now, one variable will always depend on the other variable. In this case, weight depends on the days. There are several different things to consider about the scatterplot, and these are strength, direction, and form, and these are the things we're going to talk about next. But really, a scatterplot is just a graph with points on it that relate two variables together. Okay, so what's the first thing we want to talk about? Strength of a scatterplot. What is strength? Strength determines how close the points are to creating a straight line. A scatterplot that is strong will have its points close to forming a straight line. A scatterplot that is weak will have its points everywhere. So if you look here, this is a very strong graph because those points are close to forming a straight line, versus this weak graph where it's like someone took a whole handful of paintballs and threw them up against a whiteboard. That's the difference between strong and weak. It's basically how close something is to becoming a straight line. Strength also refers to the relationship between the two variables. So if they have a strong relationship, then they have a really good a pretty good relationship between the two. Basically, one could affect the other pretty well. It doesn't necessarily have to be that way. We'll talk about that with causation and correlation. But the stronger it is, the more evident that it has a chance of one causing the other to occur. Direction. So if you're familiar with how a line works, with the slope of the line and the y-intercept of the line, basically the y equals mx plus b form of the line, it's the same thing. We know that if a slope is positive, it's going to go up to the right, and we know if the slope is negative, it's going to go down to the right. Well, a graph has a positive direction if the points rise to the right and fall to the left. So we're rising to the right, fall to the left. This is basically a positive slope. And again, they don't have to form a straight line to still have a positive correlation. You can have them all over the place as long as it's still rising to the right pretty consistently. And negative correlation would be the same thing, except for it's going to go down to the right. So remember, positive correlation going up to the right, negative correlation going down to the right. And again, it doesn't have to be like real straight on. You can have little dots everywhere as long as it's still going in that direction. Next thing we're going to talk about is form of a scatterplot. So a scatterplot can take the form of other things. Now, for my class, we just pretty much look at linears, but it can take other types of things. Like this one's a quadratic scatterplot, which is an upside down. In this case, it's an upside down U, but it's basically a U shape. And this one could be an exponential scatterplot. Now, when we start talking about correlation, we'll talk about how it only really works with linear data. So if you were to get something such as a quadratic scatterplot or an exponential scatterplot, you'd basically have to find a way to what we call straighten the data. And what that would essentially do is it would ultimately be doing the opposite operation to straighten it. Now, in this class, we're not going to do that. We don't have a need to, but it's just something for the future. If you need it. Naming the two variables. So we just talked about all the different things, all the different aspects of a scatterplot, and they're all important, and we're going to talk about them a little bit more when we talk about correlation. Naming the two variables. You may have noticed that there is always two variables in the graph, one along the x-axis and one along the right axis. So remember, we're comparing two variables every single time that we do a scatterplot. And That is important because each variable is going to have its own thing. We call the variable along the x-axis the predictor or the explanatory variable. These variables have multiple names. I don't know why. It's like in math, everything has to have 3 or 4 names and mean the exact same thing. I don't know why. Maybe it's just to make it more confusing. But, and the x-axis is the predictor or the explanatory variable. We also call the variable on the y variable the response variable. So these are both, we want to keep in mind these names. So when referred as the predictor variable or explanatory variable, we're talking about the x-axis, and when talking about the response variable, we're talking about the y-axis. And I'm going to jump this real fast. You can always think the response variable is always going to respond to the explanation or the explanatory variable. That's kind of how I remember what they are. So I think it's helpful. But if you go back up here, since the response variable depends on the explanatory predictive variable, the response variable is always the y value. So when asked, what's the response and what's the explanatory, the response will always be y and the explanatory will always be x. So which variable is the explanatory and which is the response of the two variables? The amount a person earns and the mortgage payment a person can afford. Well, when you look at that scenario, it turns out that the amount a person earns is the explanatory variable, and the mortgage payment a person can make is the response variable. And this is because the amount you can pay for a mortgage is going to directly depend on how much you make in as you earn. I know that I can only afford so much for my house. I mean, I certainly would love to have a bigger house, but it all depends on how much I earn as a teacher, which isn't that much, but I still like the job. At any rate, that's an example of how to tell whether or not something is response or explanatory. Remember, response will always depend on the explanatory variable. Alright, correlating two variables. How does one determine strength and direction of a scatterplot? We can find the R variable, which we also call the correlation variable, and that tells us the strength and direction of the scatterplot. Now, I'm going to be doing this by StatCrunch. I guess somewhere down the road, I might end up doing it with some other stuff, maybe like Minitab, maybe like Excel, or an actual regular calculator. But my students use StatCrunch pretty exclusively. There is a way to do this by hand, and I might make a video just showing that once, again, somewhere down the road. But I don't recommend it because it's got a lot of calculations to it. But yeah, there is a way to do this by hand, but we'll be doing it with StatCrunch. Now the important thing here, though, is that the R value will always be a number between -1 and 1 inclusive. And honestly, a lot of stuff that we do in stat is going to be between -1, or really just between 0 and 1, but in this case, -1 and 1, including -1 and 1. But the thing you have to be very careful with, and I tell my students this all the time, is that going towards the negative number, so getting a -1, does not mean weak. So essentially, the sign only denotes the direction. So we talked about having a positive direction and a negative direction. So if we have a negative number, that just means it's going in a negative direction. And if we have a positive number, that means we're going in a positive direction. Closer to -1 means we're getting strongly close. So really it looks like this. -1 and 1. The closer you get to -1, the stronger negatively we get. And the closer we get to +1, the stronger positive, we get. So stronger negatively, stronger positively. It's actually going towards 0. That is the thing that makes us weak. So as we go towards the 0, we get weaker. And that's kind of the thing you have to program your mind with this. Because most people think, well, as you get to -1, it's getting weaker. But no, it's not. As you get closer to either extreme, it's actually getting stronger. I should probably close my window because people are working outside, but you know, it's probably not that loud. And I kind of want to get the air. Again, not being very professional with these all the time. Let me know if it bothers anybody, and I might reshoot it. But be careful. A natural inclination is to believe that as we get close to -1, the correlation gets weaker. However, this is not the case. Always remember, getting close to 0 makes it weaker. Now, these are not official modifiers of strength. Every time I teach a class, my students always ask, well, what is the kind of the cutoff points? And in reality, the cutoff points are whatever you want to make them. Remember, statistics is one of those things where there's not always one right answer. So we can kind of modify our strengths based on where we see it. Personally, as a teacher, like I call something strong until it's like 0.6, because you know at 60% it's pretty much the lowest possible passing grade one can possibly have. And then after that, I just say things are weak. But for the idea of having something just so we can all be on the same page, we can call greater than 0.9 very strong, 0.8 to 0.9 strong, and you can kind of read all that stuff. And I made the halfway point at 0.5, where it starts being weak. Now, notice that 0 says no correlation. That's because if you have a 0, there's literally no correlation. It's just everywhere. A thing with 0 correlation would literally have everything everywhere. There would it would just be randomness. So you're not really ever going to have anything that's a 0 correlation. But if you did, there'd be literally no association between the two variables whatsoever. Okay. So we got that name, that correlation, and you know, I'm a somewhat young person, I guess. I'm not that young anymore. But anytime I see the words name that and I see something else, I want to say name that Pokemon. So it's name that correlation. My jokes are terrible. Now, what's this correlation? Well, very first thing, it's going to have two aspects. It's going to have a strength and a direction. So just looking at the top ones, I know all of these are positive. And I know all of these are negative. So that's part of it in interpreting all these. Now, I want to also determine the strength. So it's this one would be positive, and I would say strong, or you can say strong positive if you want to reverse that. There's no real order to it. For 0.5689, I might say strong, and using my modifiers from before, I would say positive, and I would say maybe slightly strong. At 0.2389, I would probably call this moderately weak. Honestly, it's pretty weak. Here's a tip for you guys as you go out. If you ever see a study with any R value, because usually they do the R values and show you. If you ever see a study with any R value that's less than 0.6, I would probably kind of look at that and be like, I don't know if you're really showing a strong relationship between your variables. I was taking a college class because teachers have to take so many classes a year, and they asked. It was literally an education class. I can't even remember. I think it was like words per minute, something or else. But the graph displayed an R value of like 0.4 something, and I was like, they asked the question, what's the thing that you kind of noticed about the graph? And people were talking about like as like age levels go up, the word count goes up or something. I can't exactly remember what it was, But my response was, well, I noticed that the R value was like 0.4, which would lead me to believe that this study isn't really a good one, because a 0.4 is not a very strong correlation, and it would lead me to believe that the two variables don't even really correlate with each other, and there's no real association between them. The response was, oh, you're a math teacher, aren't you? May not be funny, but let's keep going. So, negative, somewhat weak. Again, these aren't static. You can change them a little bit. Negative, somewhat strong. And negative, very strong. Okay, so we got that. Okay, so using the table to the right to answer the question, what is the explanatory variable and what is the response? So remember, the response always depends on the explanatory variable. So if I look here real fast, which one depends on the other? And my inclination would be that the hours it takes to finish a project would depend on the number of workers. So I'm going to label this one the explanatory. And I'm going to label this one the response. Now, we're going to calculate a correlation value using StatCrunch. When it comes to correlation, and we'll talk about this a little bit later, it actually does not matter which one is which. But when we talk about a line of best fit, it will. So, best to go ahead and just talk about it now. So, let's see. I want to do some StatCrunch. And hopefully, if this worked out, it should have flipped over onto the video and you should be able to see StatCrunch now. If not, I'm going to have to reshoot a little bit. Hopefully that's not the case. But what I'm going to do here first is I'm going to go ahead and put in the number of workers and I'm going to put in, I'm not going to put in that whole title, I'm going to put hours instead of number of workers. Call me lazy if you like, that's up to you. But I don't think you need that whole entire thing there. Okay. So, and I'm just going to go ahead and put in all of that data. Okay. And here's how I'm going to go and get the correlation for my data set. What I'm going to do here is I'm going to go to stat, and then I'm going to go down to this thing that says regression, which really anything that involves one second. That would involve scatterplots, is the word I was looking for. It's going to be with this regression. Now there is technically another way to get the correlation, but this is probably the best way for what we're going to do with all the stuff that we're going to do with it. So we're going to hit simple linear here. Now, again, technically when it comes to correlation, it doesn't matter which one's the x variable or the explanatory, and which one's the y variable or the response. But because it will matter for things later, I am going to make sure that I get the correct one. So number of workers and hours. Okay? And then I don't have to fill anything else right here for this part. I'm just going to hit compute, and I'm going to get a whole bunch of stuff here. Now there's a whole lot of information here, and if I press the arrow over, I'm actually going to pull it open just a little bit more. If I push the arrow over, you can actually see a graph with a line and all the points there. So what I want though is I want the R correlation coefficient, which is right there. So I have negative point, and I'm actually going to just take 4 decimal places. I'm not going to take them all. So what that gives me is a negative 0.9715 correlation value. So this is my R value or my correlation value. And what that tells me is that my association, which is basically a word that's kind of synonymous with the word correlation, my association is very strong and negative. And that would make a lot of sense that it's negative, just because you notice as these points go up, these points are going down. Makes sense. If I have a negative association, as one goes up, the other one goes down. It has to be going in that direction anyway. So as one goes up, the other one goes down. And again, you can see it in the graph. If you take a look at it, you have a negative slope on that line, so it makes sense to have a negative association. Okay, so let's look at another one real fast. So same thing here. I have years of college education and starting salary. And I know, there's probably people making arguments saying, hey, starting salary is not 100% dedicated to college education, and that's fine. I believe that as well. But, just because there is correlations between the two. And honestly, this would be the explanatory. This would be the response, because the more in college you make, the more you are likely to get more money. So it's going the starting salary is definitely dependent on the years of education. So what does the correlation variable say? So once again, I'm going to minimize this, and it should go right over there. And honestly, I should be able to click on this and see results and pull it back out eventually. And I probably will do that. But now I'm going to go ahead and input my data again. And again, I'm not going to write the whole variable out. If you have a problem with that, you can sue me. It won't go anywhere because, frivolous lawsuits. But that's a joke. Don't try to sue me, please. 2, 3, 3, 4, 5, 6, 6, 7, and 8. Okay. And then 445. Whoops. That wasn't supposed to happen. Get off that. There we go. 45,000, 51,000, 49,000, 600,000, 67,000, 72,000, 71,000, 8,000, or 80,000. I don't know why I say 80. No one wants to make $8,000 a year. And can you imagine making just $8,000 a year? It's be criminal. So there's my numbers, and then we're going to go again to stat, regression, simple linear. Now be careful because I have a bunch of stuff in there now. I want to pick my years, and I want to pick my starting salary, and I'm going to hit compute. And again, I'm going to get a R value, and now R correlation value of 0.9 or 0.929 So if I look back, I'm going to have that R value, which means it's very strong and positive. And the very strong just means it's got a inclination to maybe influence each other. It doesn't still necessarily have to. But as one goes up, the other one's definitely going up. There's not necessarily a direct influence, but something's happening there. Okay. Use the table to the right to answer the question again. So we got appropriate dose of medicine and weight in pounds. Now, this one specifically here, because most people will be like, oh, well, this one on the left is always the explanatory, and this one's always on the this one on the right is always the response. Not always, because in this case, the appropriate dose depends on the weight. So you have to be careful. Explanatory and response. It's actually reversed in this case because appropriate dose is going to depend on the weight. So now, again, I'm going to go back here. Going to minimize this one. Always kind of weirds me out that the X is minimizing it, not just canceling it out all the way. So again, we're going to put, oh, nope, didn't mean to do that. Let's cancel that out. So, dose and weight. Okay, so we got 200, 220, 234, 195, 350, 320, 320, 330, 315, and then 150, 167, 178, 145, 200, 204, 183. He thinks I didn't write one over there. I'm going to have to double check it. 186, 193. Yeah, I'm missing one over here. Let's go back up here. 200, 220, 234, 195, 350. Oh, there's two 350s. I need to make sure these line up correctly. Otherwise, it's just going to mess everything up. Okie doke. So now, once again, I'm going to go back into stat. I'm going to go into regression, and I'm going to hit simple linear. This time I'm going to be careful. I'm going to hit weight first because weight is the explanatory variable and dose is the y variable. I'm going to hit compute, and I get myself an R equals 0.9323. And so I'm going to get a very strong positive, which again, that just basically means as the weight goes up, the dose is going up. A negative would mean as the weight goes up, the dose would go down. So yeah, that's what the positive and very strong is. And they just very, very strong, very close to possibly forming a straight line. Okay, so some more notes on correlations. Correlations is symmetric in nature. We just kind of talked about that, meaning it technically does not matter which variable is explanatory in response. Had I flipped those around in my calculations, I still would have came up with exactly the same R value, just not the exact same line of best fit, which we'll talk about in a second. Correlation has no units. So like the last one being 0.9323 is not 0.9323 cats. It's just a number. It's not really, it has no units. And we talked about this before. Correlation describes a linear relationship. Hence, if the data is nonlinear, it will always produce a weak correlation. So what you have to do with correlation, if you want to do it to a nonlinear set of data, you have to actually do what's called straightening it. And we're not worried about doing that in this class, but again, it just means just using the opposite operation. Maybe one day I'll do a video on that one too. Beware about overstating correlation. This is where you see a lot of lawsuits start to happen in regular things. Correlation tells you a relationship between two variables. It does not prove that one variable is causing the other variable to occur. This is a phrase we say that correlation does not mean causation. You may have heard that before. Correlation does not mean causation. Just because two variables have a very strong correlation does not mean that they are causing each other to occur. For instance, as the sale of ice cream increases, the death by drowning increases. They are very strongly correlated. And if you look it up, they are very close to forming a straight line, I'm pretty certain. But clearly, just because ice cream sales are increasing, it is not causing the death by drowning to increase. Why are they correlated? Because you have this thing in the middle called a lurking variable. So the ice cream sales go up when the weather is getting warmer, which causes more people to swim, which causes more people to die by drowning. So there's really like two lurking variables that point to the next thing. So you have to be careful with saying that one, just because something has a strong correlation means that the one is going to cause the other to occur. You always have to do more experimentation in real life to determine whether or not that is actually true. So be careful. That's also why you see some pharmaceutical companies producing medicines for things, and it turns out they didn't work so well. So just gotta be very, very careful. Never conclude that one variable causes the other to occur without more research. I had a roommate once, and he liked country music, and I hated country music. And so there's actually a study that says as country music increases, the rate of suicide increases. So I tried to use that argument against him to get him to stop playing country music, and it didn't work because he knew about this rule. But yeah, it's weird. A lot of these have to do with death. I don't know why, but just keep that in mind. You can never conclude that one variable causes the other to occur without more research. Okay, so now I move to what's called the least squares regression line, which, if you've taken a math course before, you probably have seen this before. But we call it a line of best fit or a prediction line. Why all the names? Again, math has to have 3 or 4 different names for the same thing. I don't know why. But as you may have noticed, one point rarely creates a perfect line, or R points rather. I don't know why I read it as 1 point. So these glasses, I guess. R points rarely create a perfect line. So we use a least squares regression line to extrapolate and interpolate data points that we already have. So essentially, what we do is we create this line to predict what might happen in the future, as well as to kind of show how far off the data might be from our actual line that we create. These lines take the form of a regular line, taking the form of y equals mx plus b. There's a little algebra there for you. So y equals mx plus b, where m is the slope of the line and b is the y-intercept. So, create a least squares regression line to predict the data to the right. Now again, there is a hand calculation in which to do this. We aren't going to do that. Again, maybe one day down the road, I might go ahead and do that hand calculation. But we're going to use StatCrunch to do it. And the great thing about it is, the reason why I use this particular methodology through StatCrunch to get the correlation is because it already calculates the line of best fit. So if I go back to my one about workers and hours, and I go back over here, because for some reason I left it on my graph, my line of best fit, or my least squares regression line, is this one right here. So I'm going to write that whole thing out on my paper. So we got hours equals 659.55, and I'm going to round again to 4 decimal places, minus 41.6293 times the number of workers. Now, I will mention this, and I'm going to go ahead and put this back over here for a second. I will mention this, and I don't know why, but StatCrunch does not put the line in as you would normally see it. So in most math classes, you would see y equals mx plus b. However, for For a stat crunch, it's doing y equals b plus mx. I don't know why, but that's just what it does. Can't do anything about it. So you have your y variable, which is ours, which we already said. Y is our response. X is our explanatory. And then we have our y-intercept, which is this. And we have our slope, which is this. And we're going to point those out in a couple of seconds. But that's our least squares regression line. So if we go over here, we're going to create our least squares regression line again for this first example. Again, I've already done it. I can just minimize this. I can go look at my next one that I already did, simple linear regression, years, and salary, and we've got this one. That is my least squares regression line. So I've got starting salary equals 2,000, not 2,000. I am saying numbers wrong all day today. I don't know why. Maybe I should just make it a theme or something. But 20,094.595 plus 9,753.3784 times the years. So again, that is my line of best fit. There we go. Or my least squares regression line. Whichever one you want to call it, I'm pretty good with either. Okay, so now, create a least squares regression line to predict the data to the right. This is the dosage and the weight. So once again, I'm going to go back to my StatCrunch. Okay, I'm going to minimize this one. And I'm going to go back to simple linear. And I'm going to get my dose equals negative 252.6949 plus 2.999. Oh, really? It's well, we'll probably just we won't round that one up this time. Wait, technically I should round it up, but we'll keep it that way for right now. Someone's gonna be screaming in the comments one day about how I should have rounded that up. Yes, I should have rounded it up. There's probably a math person who's gonna be screaming at me too. Yes, I should have rounded it up, but I don't feel like crossing it out and doing it. It's good. It'll be fine. It'll be fine. But there's my least squares regression line. Okay. Explaining the parts of the least squares regression line. This is always the best part because it can sound really weird sometimes, especially the y-intercept. The y-intercept does not always make a ton of sense, but we still have to explain it anyway. So the two parts of a least squares regression line that we want to focus on is the y-intercept and the slope. The slope is always next to the x. When using StatCrunch, it will always be the second number. The slope tells us the rate that the line is moving. So remember, it's a rate, it's moving, it's a motion. The y-intercept is the one that is being added or subtracted, and when using... that if you flip it around. And when using StatCrunch, it's the first number you see. The y-intercept gives us our starting point and is where the explanatory variable is 0. Okay. So we're going to explain what these two things mean in the context of our problem. But the big thing to remember is this, is that the y-intercept is always going to be where the explanatory variable is 0, and that the slope is a rate that is always moving, so we have to kind of talk about it as if it was moving. So, if we go back to this, and I'm actually going to replace that one with this one because, hey, I can. I got that as my slope, or as my line of best fit. So now, what I want to do is first off, I'm going to clearly identify which is which. So my y-intercept is 659.5576. Okay, now I want to explain that in the context of the problem. So basically, remember, that is where x would be equal to 0, or in the case of us, it's where the explanatory variable is equal to 0. So, remember, the explanatory variable is the number of workers. We're going to say that at 0 workers, the job takes 659.5576 hours. Now, you may be saying, if there are no workers, the job's not going to get done at all. And my response to that is to say, remember, the y-intercept does not always make sense. You just have to kind of deal with the fact that it's not going to make sense. You and I know both that we have no workers, nothing's going to get done. You just have to write down what it means. At 0 workers, the job takes 659.5576 hours. Also, kind of a pet peeve of mine, I'll be doing a video on this eventually. The .5576 does not mean minutes. It's .5576 of hours. I see students all the time going, oh, well, that means 659 hours and like 55 minutes and 76 seconds. No, it doesn't. Don't be that person. Okay, so slope. So the slope here is minus, and we want to include the minus 6293. And also recall that we did say this had a negative correlation, so it makes sense that the slope is negative because it's going down. Remember, the association, the correlation corresponds to the slope. So what we say here is that basically for every additional worker on the job, the number of hours decrease by 41.6293. And technically, I get people every now and again who just want to keep it towards a pattern. Say, can we just say increases by negative? Sure, I guess, but that's really kind of cringy to say. I wouldn't ever say that in real life. We don't increase by a negative. Just say decrease. But if you totally had to do it that way, that's fine. But it just seems silly to me. But for every additional worker on the job, the number of hours decreases. Oh, I need to very much put a pluralization on that decreases. Decreases by 41.6293 hours. Okay, so that takes care of that. Let's go about describing the rest of our friends here. So we want to describe this one. So once again, there is my line. My y-intercept is, let's see, my y-intercept is 20,094.595, and what this basically says, at 0 years of college education, a starting salary is $20,000, 94. And if you really want to, because this is money and money just ends in a 2 decimals, you could just go ahead and say 60 to round up. Or if you wanted to keep it 0.595, that's up to you as well. It's all in your comfort level of how to do that. Totally understand if you want to change it to 2 decimals because of the money. And then for slope, we have 9,753.3784. So basically, for each additional year of education, your starting salary increases by 9,753.37. Again, if you want to change it into money, you say 3/8, and that's all good. Okay. So we got that. Then last one, and this one's the one where the y-intercept really makes no sense. So we got the dose equals negative 252.6949 plus 2.9999 times the weight. So what we're saying for our y-intercept is, first off, my y-intercept is negative 252.6949. And yes, that means at 0 pounds of weight, the dosage is negative 252.6949 milligrams. And yes, I just told you to take a negative dose, but I'm also telling you about a fictitious 0 pound person. No one in the history of all time weighs 0 pounds and is still alive. So, yes, I know this whole thing makes no sense, but you still gotta express it in words. So, my slope is then 2.9999. Yes, technically it's 3.0. Yes, any math person out there, it's also screaming in my head that I should have rounded it up. It's okay. We will move on. So, for every additional pound, the dose increases by 2.9999 milligrams. Okay, so now they're both explained and we're good. Okay. Predicting another point. When you use the least squares regression line to predict a point that is already in the data, this is called interpolation. Inside the data, inside what's already there, interpolation. When you use the least squares regression line to predict a point that is outside the data, this is called extrapolation. So outside extrapolation. That one doesn't work so well, but you know, interpolation is inside, the other one has to be outside. Then, if the prediction is below the real data, it is understated, and if it's above, it is overstated. So, once again, we're going to use our data to predict two places. So, going back to my teacher example, and I'm going to write this one down again, even though I'm looking at it on the side, because this one, my other paper's got kind of a lot of stuff on there. That is my least squares regression line again. So, we're going to use to figure out what it says about 4. So when it says about 4, we are interpolating because the data point 4 is already there. In fact, it's there twice. So we're going to just put 4 in there, and we're going to see what pops out. So let's do 41.6293 times 4. So we get 659.5576 minus 166.5172. Oops, that's not right. 1 second. So that gets me end up with 493.0404. So basically what our prediction based off of 4 workers is that it would take 493.0404 hours. And if we look at both of these, they're both understating, or this one is understating both of these numbers because that is, oh wait, I'm sorry, I did that incorrectly. These are both below it, so this one is basically overstating both of those numbers because that number is greater than both of those numbers. So in both cases, it's an overstatement of what is actually there. It's above what is actually there. Had it been underneath these two numbers, it would have been an understatement. Had it been between, I wouldn't have given you that situation because we could say it's the understatement of one and the overstatement of the other. Is what we could have said. But, so let's now extrapolate what would happen at 10 workers. And so what's going to happen here is that we're going to get a new number that we've never ever seen before. So we can't really say that it's overstating or understating because we don't know what happens at 10 workers. But what it's going to do is basically predict what should be happening. So I get 243.2646. So basically my line is telling me, hey, if you put 10 workers in, you should be expecting around 243.2644 hours. Again, I said you should be expecting around because technically speaking, this line doesn't statically predict everything correctly. As you can see, that it was overstating this. So there's a possibility that that number isn't going to be right, but it should be, if it's a good fit, it should be pretty close to being right. Okay, so how can we tell if something is a good fit? Well, there's really two different aspects that we do. It's called one is finding a residual, and that basically shows us does the least squares regression line fit the data really well. In order to find a residual, the first thing that you do is interpolate all of the data points in the explanatory variable. These act as a prediction data set. The response variable acts as the observed data. A residual is the difference between the observed and the predicted data, or observed minus predicted. We can then plot this point onto a line and get a residual plot. We're not going to do that part. I'm not worried about residual plot. But basically, if there's a similar number of positive residuals to negative residuals in the least squares regression line, it's a good fit. So, this is much easier doing StatCrunch. Why? Well, let me show you. So here's my example. I'm not going to bring back over my least squares regression line again. You've seen it a bunch of times. But what's going to happen is that this here is considered the observed data. Literally, someone put 3 people out there and found that that project took 550 hours. They took another 3 people out there, saw that it took 555 hours. Put 4 people out there, saw that it took 478 hours. So that is the literal observed. To find the predicted, what I need to do is I need to put each one of these points into my line of best fit, and I need to find out what the line of best fit is, or what the line of best fit says, what it's predicting. And then that would be the predicted value. And the residual is literally the difference between these two values. The residual is the observed. I'm going to spell it wrong, ain't I? Observed minus the predicted. So it's these values minus the predicted values at each of these explanatory values. Now, I'm not going to physically go and calculate all those into by hand. You can do that in StatCrunch, but even then, you really don't even need to do that in StatCrunch because you can do the residuals without actually calculating the prediction values. Now, I will show you real fast for the first one what the prediction values are. Now, I can't actually use my old data. What I'm going to do is still go back to regression, still do simple linear. And I'm still going to grab my stuff here. And so, if I wanted the predicted values, if I wanted to see them all I have to do is click this thing here that says predicted values. And it's going to compute those for me. In fact, we can do both. I can hit predicted values and hit shift and hit residuals. I don't want the student, I don't want that one. Hang on one second. Let's do control then. And hit control, that's the one I want. So hit control and then hit on residuals. And instead of selecting everything in between, it just selects those two. It will also give me the other stuff back, but that's okay. And I'm going to hit compute. And what it does here is it gives me the predicted values and the residuals. So basically, my prediction line tells me that at 3 workers, it should be 534.66978. And then the residual, the deduction of the residual, gives me 15.330218. Now, I could write all these down, but we're not going to really worry about writing them down on the paper. What I'm really worried about is looking at these residuals and saying, how many are positive and how many are negative? So let's see. 1, 2, 3, 4, 5 are positive, and then 1, 2, 3, 4, 5 are negative. So we'll just go ahead and slide that back over there. I get 5 positive and 5 negative. So since it's about half and half, that's saying that there was about 5 positive and 5 negative. So essentially, what this means is that it's pretty good at predicting the line. I actually don't know what happened to that one. Oh, it's right here. So my actual last video that I made cut off, and I'm hoping that this one will just reattach right at the end. So let's look at it. So 5 positive and 5 negative, which means about half and half. And the prediction line is basically a good fit for the data. Then, if I go back, so let's say I want to find the next one for example number 1. Now I'm covering it a little bit here because I'm just reusing the things I already wrote because I didn't realize that my new recording device cut off this part of it. So I'm just reshooting this right now. And so if I look, I calculated the residuals for the second part right here. So underneath this one right here. And so if we add them up, and or not add them up rather, if we count the number of positives and count the number of negatives, well, what we end up with is about 5 negative and 4 positive. So now you might be saying, hey, that's not exactly half, but we weren't going to get half with that when there's 9 points. You're not going to get 4.5. So in reality, that's just fine too. 5 negative and 4 positive. So the line is still a pretty good set of the data. Now when we go into the second one, which we'll see right here with these residuals, that comes out to be about 7 positive and 3 negative. So in reality, that one's not so great. In reality, it's not so much that that the line is too bad. Really, what's going to happen is it's probably going to overstate a lot of what you get. So something to think about if you ever were to use this line in this particular set of data. Well, where can we go from there? Well, there's another way of looking to see if the line is good, and this is called the coefficient of determination. It's also known as r squared because it's literally r squared. So it's literally just the correlation value squared. So the coefficient of determination tells us how the response variates with the explanatory variable. It basically says the variation of the response, how much of the variation of the response variable is predicted by the explanatory variable. So basically, if I get something like 9.576, then 95.67% of the variation of the response variable is accurately predicted by the explanatory variable. And I really don't know why I didn't put the word variation. It's the word variation should be in there. But this is used to determine how accurate the line is predicting the data. So where can we find this? Well, it's actually not too hard to find. If I look at my original data set for mine, which had to do with number of workers and hours done, if we go back to the original thing that we came up with results, the r squared is right there. So in reality, our r squared is 0.9437 or 94.37%, which basically means that 94.37% of the variation of the explanatory variable is being predicted by the response, which is pretty good. 90% is a good percentage. What about the other ones? Well, if I look at the other ones again, then we get, so for this one, our second set, we got 0.8639, which is 86.39%, and for our last one, we got 0.9323, which is different than the last one, right? I must have looked at it incorrectly then. It's probably a good thing that one didn't run then. But that would be 93.23%, which would mean that, for example 1, that we would get that 86.39% of the variation of the explanatory variable would be explained by the response. Or sorry, I did that wrong. 86.39% of the response variable would be explained by the explanatory. No, I was right. 86.39% of the response variable would be explained by the response. I think I said that right. I might not have. But yeah, 86.39% of the explanatory variable is predicted by the response. That's what I meant to say.